Hey guys, my name is Shreyas and welcome to Simple Chemistry. In this video, we're going to be focusing on the dual nature of matter and light. So, we kind of briefly talked about this in the background in the previous video about how scientists discovered that matter and light were actually related. So we're going to be really diving into that more here. So, let's look here. So we know that, just to recap, we know that energy can be transferred through something called electromagnetic radiation. Okay, and from there, we also know that electromagnetic radiation travels in waves. And we know that these waves consist of packets of energy called quanta. Okay, so these are the things that you should know at this point, pretty much. At the time, scientists in the early 20th century, scientists thought that there was no relationship between energy and waves and matter. However, Einstein and Planck discovered that there is a relationship, that these waves from electromagnetic radiation can either be thought of as a wave, which you've talked about, and all the wavelength, frequency, all that fun stuff, or they can be also thought, so that's the wave here, or they could also be thought of as a stream of particles called photons. So obviously in a wave, you're just seeing the energy moving up and down. You're not really seeing anything which is like substantial, something that has matter-like properties. But when you're talking about energy with the perspective of looking at photons, you're actually seeing particles. So scientists were able to make this relationship and see that waves don't, electromagnetic radiation can can be thought of as to have wave properties, like the waves we talked about before, and then also to have particle-like properties. So let me write that down. So this is called wave-like properties. And this is called particle-like properties. Okay, and this particle-like properties can also be thought of as mass, because each of these photons has a mass. Also, each photon represents one quantum of energy. So we talked about how in the previous video waves consist of packets of energy called quanta. Each quantum of energy is located in one photon. Okay. So now we know that electromagnetic radiation can be thought of as a wave and also as a stream of particles called photons. So there's two important points that, again, you want to emphasize. First is energy is quantized, meaning that energy can be only transferred in packets, and then electromagnetic radiation both displays wave-like properties and particle-like properties, okay? Now, later scientists discovered that all matter displays wave-like properties, okay? So it doesn't matter if it's just electromagnetic radiation or if it's something as big as a human. No matter what the mass is, you're going to have both wave-like properties and particle-like properties. Okay, so the relationship, the equation that shows this relationship is called de Broglie's equation. I've written here, and that's saying that Planck's constant over the mass times the velocity of any object will equal the wavelength of the wave that it produces. Now this is an important part here. Large objects such as a ball display mainly particle-like properties, while small objects such as electrons display mainly wave-like properties. So the larger the object, the more it's going to be like a particle, and the smaller the object, the more it's going to be like a wave. Okay. Now let's do a few practice problems where we actually use the de Broglie's equation. So use de Broglie's equation to calculate the wavelength associated with the basketball, which weighs 0.65 kilograms and is traveling at 12 meters per second. Okay. So what we're going to have to do is use again, go back here. De Broglie's equation is the wavelength equals Planck's constant over mass times velocity. So let me write that down. So we know Planck's constant is 6.6262 times 10 to the minus 34th joules times seconds. And then we know the mass of the object we've given is 0.65 kilograms. And the speed is 12 meters per second. And I don't want to get into the dimensional analysis of the units here, but if you look here, what's going to happen is you're going to cancel out everything, and you're going to be just left with meters. Okay. Important point to take note is whenever you're using de Broglie's equation, the mass has to be in kilograms. Okay, has to be in kilograms. You must convert to kilograms, and the speed must be in meters per second. Okay, if it's not in kilograms or meters per second, you're going to get the wrong answer. So already this answer, this question is giving us the mass of the object in kilograms and the speed of the object in meters per second, so we can go ahead and just calculate this. So let me go ahead and put this into a calculator. Okay, divided by 0.65 times 12. So our answer needs to be rounded to two significant digits, because these numbers have two significant digits while this number has 5. So our answer is going to be 8.5 times 10 to the minus 35th meters. So you can see here, since this is a basketball which has a relatively large mass, that the wavelength is going to be very, very tiny. So there's essentially like the ball is displaying more of the particle-like properties, and less of the wave-like properties. So I'm going to put a check mark here, and then okay, so it's showing more of the particle-like properties and less of the wave-like properties, okay? Because it is having more a big mass, which 0.65 kilograms is relatively big. And we can see that because the answer we're getting out here, the wavelength of the wave that's produced with the basketball is very, very tiny, okay? Now let's look here. So now we have an electron, so we should probably, since electrons are have a low mass, we should get a wavelength which indicates that that the electron is displaying more of wave-like properties than particle-like properties, so the opposite of the basketball. So let's go ahead and use de Broglie's equation again. So that says the wavelength equals Planck's constant, 6.6262 times 10 to the minus 34th joules times seconds, divided by the mass, which is 9.11 times 10 to the minus 31 kilograms, times the velocity, which is 55 meters per second. Okay, so from here, first, let's again, I emphasized this in the previous slide, the mass is in kilograms and the speed is in meters per second, so this is good, we don't have to alter it, but if it was not, we'd have to convert, okay, or we'd get the wrong answer. Okay, so anyway, so now that everything is sorted out, we can go ahead and just input this into our calculator. Okay, and we get this. So this is 1.3 times 10 to the minus 5 meters when we account for significant digits. So you can see here that the wavelength here is what? It was 10 to the minus 35, while here it's just, in this slide, it is just 10 to the minus 5. So we can see that relationship where whenever the mass of the object we're talking about is significantly less, then we're going to see a wavelength which is longer, and therefore the whatever we're looking at is displaying more of the wave-like properties than the particle-like properties. Okay, so that's pretty much all you have to know about the dual nature of matter and light. It's as simple as that.